Confusingly here, we're seeing the MD5 now, but we're seeing it printed twice. And welcome back to episode 8 of Haskell from Scratch. In the last episode, we left off reading the old MD5 out of the file that redo-ifchange was leaving for us. But we hadn't yet compared it against the new MD5 from the current run of redo. And I mentioned that even though we had put this trace show in here, we weren't seeing anything with the run of redo. We weren't seeing an MD5 printed out. So let's see if we can figure out what's going on here. Perhaps there's a problem with trace show in this instance. So if we use hput to standard error, and we show the actually this should be a string, so we don't need to show it. Let's see what we get after this first run here. Confusingly here, we're seeing the MD5 now, but we're seeing it printed twice. And if you're not sure why that is, the clue is that the first instance is wrapped in a string as if it were shown here. What's happening here is that trace show isn't being executed until the value of old MD5 is actually being used. To show this more clearly, let's say that instead of returning false, we'll do a comparison on the old MD5, and we'll just test whether it equals some arbitrary string of numbers, which it shouldn't. So we should get basically the same result. And now the MD5 is printed once here. And this is something that I'm sure trips up every new Haskell developer, or at least one who hasn't worked with a language with lazy evaluation before. But at first glance here, it would seem that laziness shouldn't be coming into play, or if it did come into play, it would change the meaning of our program. And what I mean by that is that laziness isn't supposed to affect monadic blocks like this, specifically because monads can be used for ordering effects. For example, in this case, it turns out that reading a file doesn't really matter, but what if instead of reading a file, we were writing a file and returning the result of that write into a variable or name that didn't end up getting used? We still want that write to happen, no matter what we do with the value of that action. So we can test if this is actually the case here by, let's say we write file, we'll just write out to lazy test and give it a string that I am not lazy, and try this out. And we need to, and we'll just sequence these actions here. And so now, if this write file and read file was evaluated, we should have this file lazy test here, and indeed it's here and has the text inside of it. And so my guess as to what's happening based on what I've seen of GHC's implementation of laziness is that there's a thunk here and it's not being evaluated completely, at least not far enough to get to the trace show. So this read file is being evaluated, but the trace show isn't. And another way to think about this is this block of IO monad actions is being evaluated enough to carry out all the actions, but not far enough that any pure functions being sprinkled in with those actions is being evaluated. I'm sure that's not a perfectly correct technical explanation of what GHC is doing, but hopefully it's enough to intuitively know what's going on here, and you can test that that's how this code is behaving. So let's not dwell on that any further. Let's move on to actually getting the new MD5 of the file we're looking at. As I said before, one way we could do this is using a shell command and calling out to the MD5 command, but we want to not only avoid forking another process, we also want to avoid introducing too many Linux or Unix specific dependencies in our program at this point. So I took a look on Hackage for MD5 libraries, and there are a few. One of them, Nano MD5, is appealing because it's fast, but it's fast because it links to the open SSL libraries. And at this point in the implementation of our prototype, I want to avoid introducing even that type of dependency. And so I opted for Pure Md5, which is an implementation of the MD5 checksum hashing algorithm in pure Haskell. So I think this is the first time that we are installing a package or using an external package. And so I'm going to talk about the process just a little bit here. I'm going to go ahead and cabal install Pure Md5. And the reason I'm cabal installing this instead of using something like cabal dev is that redo itself is not managed by cabal, which makes using cabal dev a lot more complicated. So for now, we'll just do a cabal install into the home directory. Okay, now that Pure Md5 is installed, let's take a look in GHCI at how to use it. The documentation mentions using the hash function as part of this crypto API package, which allows you to use hash in a polymorphic way so that you may be able to get hashes back based on the return type. And this is similar to some of the regular expressions packages, but I find it very confusing. So I'm going to go ahead and just use the MD5 function. So let's import data.digest.pure.md5. And the MD5 function works on a byte string. Byte strings in Haskell are a more efficient representation of a string, but they don't give you the benefits of Unicode and conforming to the list interface that Haskell strings do. But you'll see them used a lot because that performance benefit can be quite significant. For example, if we were reading a file with normal string functions here, like we did previously for reading the old MD5, we used read file. It's going to convert that file into a list of characters. That's no big deal when the file is small. The disk seek is probably going to take us more time than any conversion we're doing in Haskell. But for larger files, and we don't know the size of the files that we'll be dealing with to check their MD5s, we want to just read out the bytes of the file essentially and take the MD5 on that. So that's why we're using a byte string. It's also important to differentiate between lazy byte strings and strict byte strings. The reasons for using either you can find on the Haskell wiki or some other blog posts out there. But the important thing here is that MD5 expects a lazy byte string. So we'll take the MD5 of, and MD5 is a pure function, so we'll lift it into the monad, the IO monad, and then we'll use data.bytestring.lazy.read file on the file we want to read, in this case redo.hs. Oops. Let's import control.monad. Try that again. So there, hidden in the linking messages, is the MD5 of that file, and if we check it on the command line, redo.hs, it should be the same. And it is. So let's incorporate that into our code here. We're going to need data.digest.pure.md5, the MD5 function. And then what's common for importing data.bytestring, since you may need to use the strict implementation and the lazy implementation sometimes in the same module, it's common to import it qualified with an alias, And I'll just use BL to represent ByteString.lazy. So now we can just use, let's say here, new MD5 is the result of MD5 applied to our lazy ByteString read file of the dependency file. And then instead of this arbitrary string here, we'll use the new MD5. So we're saying that the file is up to date if the old MD5 matches the new MD5. So let's compile that and test it. Oh, and we have a problem that the type of the MD5 function is an MD5 digest as a result, which is not something we can compare with a string. But fortunately, the MD5 library provides a show instance for the MD5, which is what we saw printed out, which is why we saw this printed out from GHCI. GHCI uses the show instance. Okay, we have it compiled, and now let's run again. And again. And something doesn't seem to be working here because redo should figure out that it doesn't need to recompile itself anymore. So let's take a look at the new MD5 as well. We'll run it one more time, and we'll see that the MD5s actually look like they match. But there's one small difference, and that's this new line character here on the first one. So what's happening is that our redo-ifchange script, when it places the MD5 into this file, it's appending a new line as well, and we're getting that here, which is throwing off the string comparison. So we could use something like trim, which actually, if you look for it, there isn't a single standard implementation of it for strings. So various libraries have implemented their own interface to a trim and their own semantics. But we don't actually need it here. Instead, I think it's clearer just to read out the first line of this file with a function like hgetLine. But hgetLine requires us to open the file ourselves, whereas readfile handle all that for us. But that's not too big of a deal with the command withFile, which will open the file, given as the first argument, run the second argument with that handle, and then close the file for us. So let's go ahead and make sure that all of those are in scope. I don't believe withFile is exported by default. Oh, and I forgot that we need to actually provide a mode for opening the file with. So let's import the IO mode constructors, and we'll use read mode. And now redo is actually no longer using the .do script. It has recognized that the MD5 hasn't changed. So I don't think we need to print out these MD5s anymore. Oops. And now that we've made a change to the file, redo should recognize that it changed, and it did, and rebuild it again. And now it's just printing true to show us that it's up to date. So it would seem like our work here is done at this point. But if we think about it, there's at least one case that our code's not handling. What if we have a do script with, say, multiple dependencies, and then we remove one of them? The next run of redo-ifchange isn't going to know about that dependency and will leave it around in the redo target directory. Additionally, it would be good to know when we don't have any dependencies, in which case redo-ifchange is never called and it'll never create the redo target directory in the .redo directory. That way we can actually distinguish between the case that we know there's no dependencies or the case when the directory is just missing, which may have just been the first run. So it seems like the correct thing to do is to make the .redo target directory inside of redo itself instead of in redo-ifchange. I'm also going to remove this debugging line while we're at it. So let's switch back into the Haskell code. And the point at which this should happen is if we notice that the target is not up to date. So this will happen on the first run and any non-up-to-date runs after that. So one way in Haskell to do this is to use the function create directory if missing, which allows us to avoid having to catch an exception in the case that the directory is already there. And it also provides a second argument of whether or not to create all the parent directories for this directory if they don't exist, which gives us the same effect as that make-dir-p from the redo-ifchange script. And so then we just give it the directory name, which in this case is .redo, and then the target name. But this just gives us the same exact equivalent behavior from the redo script before. What we really want to do is completely remove the dependency directory before this run, recreate it, and allow a fresh set of dependencies to be put in. And this will handle the case when a dependency is removed. And to do this, we use remove directory recursive, which will remove the directory and any items within it, including subdirectories, on our target. So let's import both of those from system.directory, remove directory recursive, and create directory if missing. And you're probably screaming at this point, hey, don't repeat yourself here with the target name, the directory name. So let's go ahead and give that a name. We'll just call it something like meta-deps directory. And that's going to be .redo, and then the target. So meta-depster, and the same here. And while we're at it, we should centralize anything that deals with this .redo directory, and it turns out that another part of the code is using this same directory when it goes to read things. So let's instead make that a file path argument, meta-deps directory. We can get rid of it here in the where clause and then change it here. And then we need to still pass it in to the up-to-date call here. So meta-deps directory. So let's check if this compiles. And dep-dir is still being used here. So we'll change that to meta-depster. Okay, so this compiles, but it's going to throw an exception if the directory is missing. If you look in the documentation for remove directory, one of the exceptions that it can throw is a does not exist error. And so the first time we are working with this redo project, when there's no .redo directory, if we try and run it with the way it's currently written, we get this exception. Actually, we first get this get directory contents exception, which is being caught here, so I think this is just a misleading message. We'll see if it goes away when we catch the problem in, we catch the exception in remove directory recursive. So we already know how to use catch, and we can catch this exception and then compare with the function is does not exist error on the exception, which automatically tells the compiler which type of exceptions we're interested in. So all we want to do is say that if this is a does not exist error, then we don't care, we'll just return nothing. But if it's a different type of exception, we want to rethrow it. So now it turns out that there's actually a function catch just, which was designed for just this case. So the first argument to catch just is a predicate that determines whether or not this is a exception that we're interested in. So we can move this part from down below. If does not exist error, then, and what it expects back is a maybe value. So a just in the case that it's an exception that we want to deal with, or nothing in the case that it's not. And we still have to have an exception handling block here, but now it can just be this. And now this first argument here seems a little strange. We have a Boolean value, and then we're returning just in the case that it's true and nothing in the case that it's false. And there should be some sort of function to do that for us. And it turns out that there is. It's in control.monad, and it's called guard. And technically what it does is return m0 in the case of a false result, but in the maybe monad, that's nothing. So what we can write here instead is guard is does not exist error. So let's try compiling that and see if it takes care of this get directory contents problem. Oops, does not exist error is part of system.io.error. Let's, just in case it's there, we'll remove the .redo directory, and then we'll run this again. And now this time it's behaving as normal, so that exception was just confusing. Maybe Haskell actually tries calling get directory contents in the case of create directory if missing, or sorry, remove directory recursive. Okay, so now it finally seems like we're at the point where we're ready to convert this redo-ifchange into Haskell, which, since all it's doing is this loop here with some MD5 writing, should be pretty simple. But there's an important behavior of redo-ifchange that I've neglected up until now because we haven't needed to use it, but I want to show you here. Let's say that for some reason our redo implementation wanted to use the readme.txt file. You know, let's say we had some template Haskell or some macro of some sorts that read the contents of readme.txt into the script so that it could print it to the console if given a help switch. It's not something we're going to implement, but hypothetically we could. And let's also say that readme.txt was not built yet. So now if we run redo, and whoops, before we can even deal with this, here is another problem with our current implementation. Readme.txt is a dependency, but we haven't found out about that dependency because we've left off an important implementation detail, and that is that a redo target depends on the do script itself. And so what this means is that we're going to need to write out the MD5 file for the do script, which we don't have at this point here in redo-ifchange. We're going to need to do it inside of redo itself. But fortunately, we have all the tools we need to do this already. We already have MD5. So let's actually just take this line we got here, move it into the redo prime implementation, and we can just write out the result of that. Write file, and we're going to write to the meta dependencies directory for the do script, which in this case is in the path variable. And again, we need to show this MD5 here. But this show and these MD5 calls are all a little bit confusing. What we could do to make this a little bit better is write a helper function, MD5 prime, that takes a file path and gives us a string. So the implementation would be would look something like this: show of MD5. This is I'm just copying what we have here in up to date, and so now we should be able to replace this with MD5 prime, and we should be able to simplify this here to MD5 prime of the dep. And we still need the dependency here. We still need the path here, and I've got the wrong name here. This is going to be of the path. So let's give that a try. And let's ignore the error about MD5, the readme.txt error here, and let's see what happened with the redo directory once we run this one more time. So now inside of the redo directory, we have a checksum for the actual redo script, redo.do, that was put there by this line in the redo file. So at this point, we've gotten into a weird state because of this readme.txt. So let's remove that for a second. And I'm also going to remove it from the dependency directory. And so now when we build redo, it builds once, builds again, and strangely keeps building. Let's see what's going on with the okay, so that took me a little bit to figure out that I left this show in here, which works just fine on a string, and adds some double quotes, which is going to throw off the comparison. So let's try again now. And now we're getting the desired behavior. So if we add this extra dependency here now redo notices that the do file has changed, and then it needs to go through and do its work again. But the problem is that readme.txt doesn't exist. We have a rule for building it, but redo-ifchange doesn't know anything about that. However, in the actual implementation of redo, or the design of redo, redo-ifchange should behave like redo when it encounters a dependency. It shouldn't just treat it as a simple file. It should go ahead and try and rebuild that dependency if a rule for rebuilding it exists. So I'll give you some time to think about how we could go about implementing that in between now and the next episode. As always, thanks for watching, and I'll see you next time.